Hello everyone, this is Sai Krishna. Today let's discuss about Shattermap, a revolutionary internet backbone monitoring system. Let us discuss about this topic. What happens when a single fiber optic cable breaks at an internet backbone? How do massive networks figure out in milliseconds whether you are still connected? Today we are exploring Shattermap, a game-changing data structure that redefines how the internet monitors itself in a real time. The, Here we can discuss the problem of this solution, and the internet backbone handles hundreds of thousands of links and updates every single second that connects being added, removed and verified constantly. The challenge in these traditional data structures like union find were never designed to handle deletions efficiently. Meanwhile, methods like BFS, breadth first search, are incredibly slow when you are running millions of queries per second. Here we need something fundamentally different. Let us discuss how Shattermap works. Shattermap genuine lies in a simple observation about real backbone networks. 99% of edges are part of cycles. They are redundant. He highlight reinforcement versus edges. Edges fall into two categories. Reinforced edges are part of cycles and removing them does not disconnect anything. Stretches edges. Bridges removing them could break the network. These are very important in a network. In a 30,000 edge network, only 0.27% were bridges. Remaining are edges. This is where Shattermaps gets brilliant. For the 99.7% common case, deleting a reinforcement edge, it operates in constant time 0.0 big O of 1 instantaneous. But what about stretch edges? Which one is deleted? What we call a fracture. Shutter maps trigger something called bidirectional component verification. Instead of checking the entire network, two search waves read simultaneously from both connection points. If they meet, face false alarm, and is internal path an alternate path exists. No split. If one exists before meeting the other, a true split is confirmed. The genius complexity is proportional to the smaller component, not the entire network on a 90,000 node network. This can be 1 lakh times faster than the traditional methods. In a real world testing against classical data structures on a 90,000 node backbone with 3 lakh edges, Shattermap query performance is less than 0.01 milliseconds. Union find is 0.95 milliseconds, but they can't handle deletions. Traditional BFS 3.319 million milliseconds for the same queries. The Shattermap shows the efficient way to perform that. Shattermap doesn't just query faster, it proceeds 40,000 deletions in 4.43 milliseconds while maintaining complete accurate connectivity. The state backbone grade performance massive scale real time precision. Why it matters? When a fiber cable in a underwater trench or a router fails in a data center, ISP needs to know immediately if you are still connected. Shuttermaps makes that possible at a scale. This means faster internet outgate detection, automatic rerouting in milliseconds, not seconds, monitoring 9,000 plus nodes networks without massive infrastructure costs. It is just faster. It's enabling entirely new possibilities for network scalability. Shattermap proves that sometimes the best innovations comes from understanding by your specific problem. By recognizing that backbone networks are sparse and most redundant, researchers built a structure optimized for reality, not theory. The result, a data structure that's as simple as fast as union find, but with the power to handle the dynamic real-time demands of 21st century internet infrastructure. The Shutter Map builds a faster efficiency than any data search algorithm like Union Find and others. Thanks for watching. If you are curious about network algorithms, data searches, or how the internet actually works under the hood, subscribe for more deep videos. See you next time.